Let us compare the reactivity of the alkali metals and the alkaline earth metals. As an experiment, we will put 20 cubic centimeters of water and 70 cubic centimeters of hexane into each of 4 graduated cylinders. Next, we will add small samples of the following metals to the cylinders. 1 metal to each cylinder: sodium, potassium, magnesium, and calcium. In all the cylinders, we can see the metal effervescing with the release of gas. However, the speed of reaction varies among the samples and decreases in the order potassium, sodium, calcium, magnesium. The high reactivity of alkali metals is due to their tendency to lose their outermost electrons and change into cations. In the course of a chemical reaction, the atoms lose their valence electrons to achieve the stable configuration of a noble gas. Starting with lithium and moving down the group, the reactivity of successive alkali metals increases. The larger the atom, the greater the distance between the nucleus and the valence electron, and the easier it becomes to remove the electron. The electrostatic attractive forces between the nucleus and electrons decrease with increasing distance between them. That is why the higher the number of the valence shell, the more reactive a given alkali metal is. Removal of 2 electrons requires more energy input than removal of 1, so alkaline earth metals are less reactive than alkali metals. The reactivity increases down this group as the atomic number increases, because the growing number of electron shells results in weaker attractive forces between the valence electrons and the nucleus.
Compounds of S-block elements have an ionic structure, in which group 1 elements occur as Li+, Na+, K+, Rb+, and Cs+ cations, and group 2 elements as Mg2+, Ca2+, Sr2+, and Ba2+ cations. The salts of elements in the S-block have an ionic structure. For example, sodium chloride is composed of sodium ions and chloride ions arranged alternately in all directions and at a constant distance apart from one another. Sodium chloride occurs in nature in the form of deposits of the mineral known as rock salt and as a component of seawater. Seawater also contains soluble salts of magnesium, calcium, and potassium. While all alkali metal salts are soluble in water, the salts of alkaline earth metals have varying solubilities. For example, the commonly occurring calcium carbonate and magnesium carbonate are the main constituents of sedimentary rocks, limestone and dolomite. Hydrated calcium sulfate 6 occurs in nature as the mineral gypsum, used in surgery for making casts for protecting fractured bones. Electronegativity is a measure of the ability of an atom within a chemical compound to attract electrons. The more electronegative element becomes negatively charged, while a positive charge forms on the less electronegative element. In the extreme case, the separation of charge leads to the formation of an ionic bond. Fluorine, with its electronegativity of 4, is the most electronegative element. The least electronegative element is cesium, which has been assigned an electronegativity value of 0.7. Sodium reacts violently with water at room temperature. During the reaction, a large amount of energy is released. Note that a piece of sodium added to water floats on its surface because it has lower density. The considerable amount of energy released by the reaction melts the metal. The reaction produces sodium hydroxide and hydrogen gas. The process can be written as follows, and using ionic notation. Since sodium hydroxide is an ionic compound, it undergoes complete dissociation in water. As a result, its solution is strongly alkaline and turns phenolphthalein red. The hydroxides of group 1 metals are strong bases. Their crystals have an ionic structure consisting of metal cations and hydroxide anions. The hydroxides of alkali metals with high atomic numbers have the strongest ionic character because they have the highest electronegativity difference between the metal and oxygen. Beryllium hydroxide has amphoteric properties, and magnesium hydroxide is a medium-strength base. But beginning with calcium hydroxide and moving down the group, the hydroxides of successive metals have a similar basic strength to alkali metal hydroxides. The alkalinity of the hydroxides increases down the group as the electronegativity of the metals decreases.
Let us investigate the water solubility of calcium, magnesium, and sodium hydroxides. We will do an experiment for this purpose. We add equal small amounts of calcium, magnesium, and sodium hydroxides to 3 separate test tubes. Next, we add water so the test tubes are 1/3 filled. We shake the test tubes vigorously. Magnesium and calcium hydroxides are partially soluble in water, while sodium hydroxide dissolves in water totally.
Group 1 and 2 metals react with oxygen to give a variety of products, depending on which metal is used. Atmospheric oxygen reacts with lithium to give lithium oxide, Li2O. With sodium to produce the peroxide, Na2O2, while the remaining metals, potassium, rubidium and cesium, form superoxides, MO2. All these compounds form ionic crystal lattices consisting of metal cations and appropriate anions. Oxides as crystals contain oxide ions, O2-, peroxides have peroxide anions, O2-2-, while superoxides contain superoxide ions, O2-. Alkaline earth metals with lower atomic numbers react with atmospheric oxygen to form simple oxides having the general formula MO. Combustion of strontium and barium leads to the formation of considerable quantities of the peroxides of these metals. The oxides of alkaline earth metals are ionic compounds except for beryllium oxide, which is characterized by partly covalent bonds.
We will do the following experiment to obtain potassium superoxide. We place a little piece of potassium on a small aluminium tray and place it in the burner flame. At a high temperature, potassium initially melts and then undergoes a spontaneous exothermic reaction with oxygen from the air. When the product has cooled down, we collect it from the spoon. The compound obtained is potassium superoxide, a white crystalline solid. The sulfate 6 of group 1 metals are water-soluble. The sulfate 6 of group 2 metals vary in solubility from the readily soluble beryllium sulfate to the practically insoluble barium sulfate. This means that the solubility of group 2 sulfates decreases as we move down group 2.
The dissolution of a crystal of a salt in water is accompanied by a process whereby the ions that make up the salt become surrounded by water molecules. This phenomenon is termed hydration. Magnesium sulfate 6 is readily soluble in water because of the energy of hydration of the individual ions is sufficient to overcome the forces of electrostatic attraction in the crystal lattice of the salt. However, in barium sulfate, the interactions between the ions in the crystal lattice are too strong in relation to the interactions with water molecules, which is why this compound is insoluble. Limestone, marble and chalk are all forms of the same chemical compound, calcium carbonate, but they have different structures and contain different impurities. Limestone originated from the remains of marine organisms living in seas and oceans millions of years ago. Marble was formed by recrystallization of limestone. It is a valuable ornamental and building material. Chalk, one of the purest forms of limestone, is a soft and crumbly rock. It is used in ceramics and in the chemical and paper industries, also in architecture. On losing its 2 valence electrons, beryllium becomes a very small cation. The considerable charge of the beryllium 2+ ion, concentrated within a small space, is the reason for the unusual properties of beryllium and its compounds compared to other group 2 elements. All beryllium compounds have a largely covalent character. A typical example is beryllium chloride. It has a relatively low melting point, 405 degrees Celsius, dissolves in organic solvents, and is a rather poor conductor of electricity in the molten state.
Let us investigate the amphoteric properties of beryllium hydroxide by means of an experiment. We add about 5 cubic centimeters of beryllium sulfate 6 solution to a tube and then add sodium hydroxide solution drop by drop until a precipitate forms. Divide the suspension obtained into 2 parts and separate the precipitate of beryllium hydroxide from the solution by centrifuging. A solution of hydrochloric acid to one portion and sodium hydroxide solution to the other portion. Beryllium hydroxide reacts with hydrochloric acid to give beryllium chloride. Beryllium beryllium hydroxide also reacts with sodium hydroxide to produce sodium berylate. This means that beryllium is part of the anion in this compound. Beryllium hydroxide shows both acidic and basic properties. We say that this compound has amphoteric properties.